It's Saturday, December 28th. My name's Juan Brown. You're watching the Blanco Lirio channel, and today we're discussing the F-100, the Fokker F-100 crash that occurred in Kazakhstan yesterday, 27 December. We'll go over the facts as we know them so far, and then we'll have a little discussion on the background of the Fokker F-100 and a little review from a pilot's perspective of what this crew was up against. Facts as we know them so far from Aviation Herald, Simon Radecki's website. The BEK F-100 at Almaty on December 27, 2019 lost height shortly after takeoff and impacted building after two tail strikes. A Beck Air Fokker 100 performing flight Z9-2100 from Almaty to Astana, Kazakhstan, with 93 passengers and 5 crew departed Almaty's runway 05 right. There's two large parallel runways at Almaty. At 0721 local, that's right around sunrise. It may have been even a little bit before sunrise. But lost height shortly after departure, impacted ground, broke through a concrete wall fence and impacted a building. No fire broke out. The aircraft broke into several sections. 66 people were taken to the hospital. 12 people were confirmed to have perished. 12 people remain in hospital care. 74 people survived with no or minor injuries. Kazakhstan Civil Aviation Authority reported the air operator certificate of Beck Air was suspended on December 27, 2019 following the accident. The accident aircraft had entered service on April 8, 1996. Its airworthiness certificate was last reviewed on May 22nd of 2019. The captain was 58 years old, the first officer 54 years old. Both held ATP, air transport pilot, licenses. The captain has died as a result of the accident. The first officer remains in critical condition. Kazakhstan's Deputy Prime Minister reported preliminary results by the investigation commission suggests the aircraft struck its tail onto the runway surface twice with a distance of 300 to 400 meters in between the two tail strikes. At the end of the runway, the aircraft turned sharply to the right. The landing gear was retracted at this point already. The runway conditions were perfect, however. The Commission is looking into human error or technical reasons. The flight data and cockpit voice recorders have been recovered. A survivor reported the aircraft climbed a little bit, began shaking, then a collision occurred. Someone opened the emergency exit and the passenger got out. Another passenger reported the aircraft had just rotated and was beginning to gain altitude when the aircraft rolled left, then right, then an impact occurred. The overwing exit was opened. They crawled out of the aircraft via an icy wing. Everyone on the wing slipped on the wing. The passengers helped each other to get off the wing. The pilot of an aircraft departing Almaty about 3 hours before the accident reported that during about 2 hours, minimal white frost had developed on the slats and on the tanks of his aircraft. The Fokker doesn't have leading edge slats. More on that in a minute. However, other aircraft having parked overnight had accumulated significant ice. During departure, while climbing through 1,000 feet AGL, a temperature inversion occurred with a temperature rise of about 11 degrees centigrade. The ADS-B data transmitted by the aircraft's transponder suggested the aircraft became airborne, climbed to between only 50 to 100 feet AGL, veered right, and impacted the buildings, abeam the runway about 3,000 feet, about 3,000 meters, 10,000 feet down the runway 05 right. Photographic evidence puts the final position to the right side of the runway centerline, about 2,500 feet or 750 meters past the end of the runway. The runway itself is 14,400 feet in length. Runway 05 right, the big runway on the right, was the departure runway. So right away, investigators are looking at another possible case of icing on takeoff, though investigators need to eliminate all the other possibilities in a thorough investigation before they narrow it down to icing on takeoff. So let's discuss a little bit about the Fokker F-100 and about icing on takeoff. The weather at the time of the accident was reported as mist with a temperature of minus 12 degrees Celsius and a dew point of minus 13 degrees Celsius. Remember, when the temperature and dew point spread is within about 2 degrees of each other, that means the air is very moist. You've probably got fog in the area, and with the temperature below freezing, that could be freezing fog or easily plenty of frost. The Fokker F-100 was a popular design produced in the 1990s by the Fokker Aircraft Company, the same Fokker Aircraft Company that produced some of the greatest aircraft all the way back in World War I. In all, there were 283 Fokker F-100 aircraft built, and by 2017, there were still 113 of them flying. At American Airlines in the United States, for years they had one of the largest fleet of Fokker aircraft, over 74 aircraft, and they operated the F-100 fleet from 1991 to 2002. Before investigators narrow this down to icing, they're going to have to look at a lot of things, including the loading of the aircraft, the flap setting of the aircraft for departure, the power setting of the engines on the takeoff roll, the trim setting, as well as the condition of the runway, though the minister said the condition was perfect, whether there was slush on the runway or not. But based on the passenger reports of slipping on ice as they were trying to get out of the aircraft over the overwing emergency exit, that's going to lead these investigators to look at possible wing contamination prior to takeoff. Though the Fokker was a popular aircraft in the 100-seat category, it does have a bit of an accident history, particularly regarding icing. The first one where we learned so much about airframe icing, particularly on the Fokker aircraft, was a Fokker F-28, the predecessor to the F-100, back in 1989 with Air Ontario 1363. Extensive investigation was done following that accident, and I'll post a link to the data below. And once again, we got to relearn all that we have learned from these previous accidents. Again, in 1993, a Macedonia Airlines Flight 301 had a problem with ice on takeoff, crashed. And as late as January 2007, Air France Flight 7775 had a very similar sounding scenario. Here's a picture of the Air France Fokker 100 accident aircraft from 2007. There were no fatalities. Folks I know that have flown the Fokker before, and maybe there's some of you out there can corroborate this, they really enjoyed that aircraft. However, they were well aware of the fact that the Fokker has a fairly critical laminar flow wing when it comes to icing and icing contamination. The Fokker aircraft does not have leading edge devices. It does not have leading edge slats. Most airliner type aircraft have, well, let me get a standby, let me get something here. Here we go, the UMX Timber. Most airliner type aircraft have leading edge devices or retractable leading edge slats. On this model, they're fixed on the leading edge of the wing, giving the wing more camber and more lift. Typically on an airliner type aircraft, when you select flaps 1, the only thing that moves usually is the leading edge devices if it's so equipped. When you select the next notch of flaps, the leading edge devices usually extend to an even further or fully extended position, and then the trailing edge flaps begin to lower, all the way down to the full flap setting where you get full trailing edge flaps along with the fully extended leading edge slats. And these leading edge slats have some blow-up capability in the event that you should overspeed them. But the Fokker F-100 has no leading edge devices, and so it has a unique airfoil designed solely by Fokker. I think it's called the Fokker 12.6 airfoil. It is not a standard NACA, who's NACA stand for? It's not a standard NACA airfoil, National Advisory Committee for Aeronautics airfoil that's found in the list of NACA airfoils. It's an airfoil unique to Fokker. Most wing designs on most aircraft are designed to stall at the root first through a combination of wing design, twist, and airfoil shape throughout the span of the wing. A stall will typically progress at the wing root first and progress out towards the tip. This is so that you can maintain roll control of the aircraft with the ailerons and get plenty of stall warning initially before you lose control of the aircraft. In the event that the wing is contaminated, you are disrupting the laminar flow over the wing. You have violated the original ops spec of the aircraft. The wing will stall at a much lower critical angle of attack. Remember, a wing or aircraft can stall at any airspeed or any attitude, but only at one critical angle of attack. But by contaminating the wing with frost, ice, or snow, you are changing the critical angle of attack of that wing. And of course, the critical angle of attack is that angle of attack at which the wing begins to stall. On airliner aircraft, you have a thing called a stick shaker to help warn you that you're stalling the aircraft. We've talked about this before. That's the device that's mounted right onto the column and sticks the shake vigorously to remind you that you are close to exceeding the critical angle of attack of the wing. That stick shaker is actuated by the angle of attack vanes, or the input to that stick shaker is through the angle of attack vanes mounted on the side of the front of the aircraft, and is set at a predetermined angle of attack based on the configuration of the aircraft. When you contaminate the wing with ice and snow on it, that angle of attack stick shaker program does not take that into account. The program is only programmed for what it knows for a clean wing. In other words, once you get a stick shaker with a contaminated wing, you may already be deep into a stall on that wing. So what investigators are also going to be looking at is what was the crew actions before the accident. Did they get the aircraft properly de-iced before they departed? I believe there's an airworthiness directive specifically for the Fokker aircraft that the pilot needs to do a tactile inspection of the top of the wing. He needs to physically take, when the conditions are sketchy like this, when the temperature dew point spread is very close and the temperature's below freezing, the pilot, usually the FO, has to do the pre-flight inspection of the aircraft and physically inspect the top of the wing for ice or contamination. You got to be able to feel it. The problem is the Fokker F-100 wing is up pretty high, and if you're a short pilot like me, you're scrambling around the airport to find a step stool to get up high enough to get a good tactile inspection of the wing. You can go into the cabin and try to shine your light in the dark. It's a pre-dawn departure. You're trying to shine your flashlight through the passenger windows and look down at the top of the wing through the scratched up passenger windows. That doesn't qualify. You got to do a tactile inspection with your hands to feel if there's any ice or contamination on the top of that wing. Another thing that can affect ice accumulation or frost accumulation on the top of the wing is your fuel load. Is your fuel cold soaked from a previous flight? In those kind of conditions, typically you'll see some frost on the bottom of the wing underneath the fuel tank from the cold soaked fuel, creating frost on the bottom of the wing. That's not usually a problem. It's the frost on the top of the wing from the inclement weather that is a problem. Did you recently fuel the aircraft up with fuel that was slightly warmer than the rest of the airframe and thus maybe melted the fuel around the wing tank area? And did you inspect outside of that fuel tank area with your fingers to see if there was frost on the top of that wing? Now let's talk a bit about what the crew faced once the fateful decision was made to take off. Assuming everything worked correctly, most airline aircraft have a takeoff warning system to warn you if you do not have everything set up properly for takeoff. It takes into account things like flap setting, power setting, pitch, trim setting. On a normal airline takeoff, you got a series of decisions to make. The first decision typically comes at 80 knots. There's an 80 knot call out. If you have any kind of problem at all, you could do what's called a low speed abort, reject the takeoff, at or below 80 knots and get the aircraft stopped just fine on the runway remaining. The second decision you have to make is V1 takeoff safety speed. This is considering balanced field and a lot of other mathematics, but basically you got to make a decision as to whether you're going to reject this takeoff or continue the takeoff, and that call comes at V1. Right after V1 is rotate. That's when you pull the stick back and begin flying away from the ground. One of the caveats of V1 takeoff decision speed, it's not only the minimum speed that you need to lose an engine and continue the takeoff and safely have enough airspeed to climb out on one engine, it's also telling you that's the maximum speed that you can attain and still get the aircraft stopped if you decide to reject the takeoff in the remaining amount of runway if you're on a balanced field.
Here's an illustration of balanced field length, where the takeoff distance, the ability to take off and accelerate under two good engines, lose an engine at V1, continue the takeoff, and depart, clearing the end of the runway at 35 feet. That distance is the same distance as reaching V1 and stopping the aircraft in a rejected takeoff.
So what's the typical cadence from 80 knots to V1 rotate? And by the way, the Fokker, being a smaller aircraft, has a pretty low rotate speed. I would think it was somewhere around 120 knots or so, and the runway is over 14,000 feet long. So by the time V1 rotate comes around, you probably have a bit of runway left out in front of you. But the decision is critical. Here's the typical cadence. 80 knots to V1 rotate. Now you got a decision to make. You rotate the aircraft right away. That's when the crew first discovers they have a problem with this aircraft. They rotate the aircraft and immediately they can tell this aircraft is unwilling to fly and it's probably beginning to already shudder and stall. What can you do at that point? Your training has taught you very effectively that you are beyond V1 takeoff safety speed. You should continue the takeoff. However, you could make a very fateful decision, a very instantaneous decision, a decision that would take about 1 or 2 seconds, much longer than what I'm talking about describing it here. You could elect to cut the power and crash straight ahead in the runway amount remaining and whatever is out beyond that runway. In other words, you have a decision to whether do you want to abort this takeoff beyond V1 safety speed and crash straight ahead and go off the end of the runway slowly, or do you want to try to continue this takeoff and potentially crash well off the end of the runway at a very high rate of speed? A very, very tough decision to make. The whole idea for pilots is you want to use your superior judgment long before deciding to take off instead of trying to exercise or demonstrate your superior flying skills once you've made a bad judgment call by jamming yourself into this corner. One other thing crews may be able to do in this particular situation where you rotate the aircraft and you can tell that the aircraft is not ready to fly is you could attempt to milk it off of the runway with just very light rotational forces and attempt to accelerate further in ground effect before flying the aircraft away from the ground. But again, you don't know this is a problem until you do your standard rotation. You do your typical rotation move, and it's a couple of degrees per second, raising the nose up to capture the flight director. You've already got into the stalling regime of the aircraft with its contaminated wing. You're already way behind the power curve. Your chances of saving it at this point are slim to none.
Here's a graphical representation of the effects of a contaminated wing from the 1989 crash of the F-28 Fokker in Ontario, Canada. On the vertical axis is increasing lift capability. On the horizontal axis is increasing airspeed. The three diagonal lines represent the degradation of the lifting capability of the wing due to ice and contamination. The dashed line represents the aircraft accelerating down the runway once the aircraft rotates on a contaminated wing, it immediately exceeds the lifting capability of that heavily contaminated wing. Due to the disruption of the laminar flow of the wing caused by the ice.
So as we get more information, I'll let you know here. Thanks again for your support of this channel. Check your subscription setup on your account there, as YouTube has been moving some things around and a lot of folks are finding themselves unsubscribed when they didn't unsubscribe. Also, thanks for your support on Patreon. As we get more information, we'll let you know. I'm still working on the Atlas Air 3,000 pages of documents. I'll have that to you next week. Right now, I got an appointment with an 8-year-old boy that wants to go dirt bike riding, and that's what we're going to go do. See you here. Come on, Pete, let's go. What do you see? What do you got?
It's ice.
Copy that. Here it come. What you got here, Pete? What is it? Yeah, you know kind of what they call that? Hoarfrost. See how the moisture in the ground comes up? Do you think that's slippery to ride on? Have you slipped on it yet? Not bad. Look, it's all over out here. Yeah, it's all over. Look at that. That's just pure mud, boy. That's slickery mud there too. Red slick. Fortunately, you got the no tears knobbies on, huh? Switch on. There you go. That helps, don't it? Does it help to have the switch on? Did you run through your pre-flight checklist?
Yeah.